All the electricity generation methods you've heard of so far actually work on the same principle, a heat transfer system. We generate heat in some way, use that heat to produce steam, and then generate electricity from that steam through turbines. This is why thermal and nuclear power plants are often built near seas or lakes and always have white steam coming out of them. We compress the steam, send it to the turbines, and voila, electricity. Even the much-praised future energy sources like tokamak fusion reactors work on the same principle. So despite all our technological advancements, we still don't have a commercial machine that converts energy directly into electricity. At least not until now. Think about it. When did we first start using steam to generate electricity commercially? Our man is British engineer Thomas Newcomen. The year is 1712. Yes, you heard that right, 1712. This clever engineer developed a steam-powered pump to extract water from a tin mine in England. Now it's 2025, we're fusing atoms to produce energy, but we're still using almost the same technology from 1712 to convert that energy into electricity. Doesn't that seem a bit odd? We're landing rovers on Mars, bringing rocks from the dark side of the moon, and using GPS for free with hundreds of satellites, yet we still generate electricity with 300-year-old technology. Even the dynamo on your bicycle produces electricity without steam. So why does a massive nuclear power plant still need a steam turbine? No matter what you do, when you try to generate electricity with a steam turbine, energy loss is at least 40%, practically around 55%. Now, check your latest electricity bill. Mine is around $2,000, and I'm paying half of that because of the inefficiency of the technology used. Imagine this on a national scale, or global. So why are we still sticking to this method? The answer is simple. It's easy to implement, there's an established industry around it, and regardless of the energy source, you can apply the same method. The biggest reason is the lack of alternatives. In science, even if you know your theory is flawed, it's a tradition not to discard it until a better one comes along. Newton's theories had known gaps, but no one voiced them until a better alternative emerged. Another issue is what the English call the sunk cost fallacy, the tendency to avoid switching to a better and more efficient option because of past investments. Sound familiar? Have you ever thought that our electricity bills could be half of what they are because of the return time on investments in fossil fuels? Putting aside the fossil fuel policies of the new U.S. administration, things seem to be changing in electricity generation. A technology that eliminates steam and turbines to convert energy directly into electricity is not here today, but it's not too far off either. Unlike traditional tokamak or laser-based fusion technologies, which are still experimental, a system using the magneto-inertial fusion method, which harnesses fusion to directly generate electricity, is now on scientists' radar. You heard it right. Electricity generation without turbines is called magneto-inertial fusion reactors, or MIF for short. So, what is MIF? The easiest way to explain it is by comparing this new system to existing tokamak fusion reactors. First, this system uses helium-3 and/or deuterium as fuel. While classical fusion reactors only need deuterium, helium-3 or a mix of helium-3 is preferred here. This choice ensures a neutron-free reaction. What does neutron-free mean? A neutron is a fundamental particle in the atomic nucleus with no electric charge. A neutron-free reaction means little to no neutrons are produced during fusion, which is great news for radiation shielding. This means cleaner and safer energy production. Classical tokamak or nuclear power plants need vast areas for radiation isolation, but this new system requires much less of it. If you're going to perform helium fusion using only helium-3, you need to combine two helium-3 atoms. This fusion produces helium-4, 2 protons, and lots of energy, with no radioactive waste. Adding deuterium results in some radioactive waste, but much less than classical deuterium-deuterium fusion. Then let's only use helium-3 for no waste, you might say, but the problem is that helium-3 is scarce and expensive on Earth. While abundant in the universe, on Earth, it's obtained from nuclear reactors or natural gas fields with highly advanced technology, making it costly. Mixing it with deuterium makes the process more feasible. Or, from the moon. It's said that there's over 1 million tons of helium-3 on the moon, enough to power humanity for thousands of years. The moon is only 363,000 kilometers away. Now we understand why the US, China, India, Japan, and Europe are so keen on the moon, and why China spent huge budgets in 2024 to bring samples from the moon. Or why Astroforge, a company focused solely on lunar mining, received $40 million in investment in 2024. According to Mordor Intelligence, $23 billion will be invested in lunar mining by 2038. Let's leave these topics for another video and continue. Yes, if you want to generate electricity without steam and turbines, you need helium-3, and getting it is no easy task. Alright, you have helium-3 and deuterium, but what do you need to do differently to generate electricity directly? In a classic tokamak fusion setup, which we still can't fully achieve, the process goes like this. Hydrogen isotopes are injected into a special reactor chamber, where plasma is confined in a massive magnetic field, forming a toroidal shape. This magnetic field heats the plasma to about 100 million degrees Celsius, preparing it for fusion. Essentially, you crank up the heat, suspend the hydrogen isotopes in a magnetic field, and wait for fusion to start. If you're using MIF, how does it work? First, you need not one, but two plasma rings containing helium-3 that haven't fused yet. These plasma rings, or plasma beads, are prepared to generate a magnetic field. These plasma beads are accelerated toward each other at high speed, ready for collision. These plasma bubbles, magnetic fields at millions of degrees, are rapidly compressed by classical pressure. At the moment of compression, helium-3, or a helium-3 deuterium mix, begins producing protons due to heat, magnetic fields, and pressure. If these protons are directed into a special magnetic field, they can be converted directly into electricity through electromagnetic induction, generating vast amounts of electricity. In simple terms, high-energy protons interact with a magnetic field and slow down, releasing energy directly as an electric current. Add pressure and helium to tokamak fusion reactors, and welcome to the world of MIF. So, why choose MIF over tokamak? MIF offers the possibility of fusion without reaching the colossal energy levels required by tokamaks, which is a big advantage. It also doesn't need massive, costly construction like tokamak reactors. Without steam and turbines, it's far more efficient. The game changer is that one day, MIF reactor could be miniaturized to the size of a phone battery, providing virtually infinite energy for human lifetimes. Imagine cars running forever, or your home powered for 100 years with a phone battery-sized energy source. This technology is currently the only one that could make that happen. Where are we now? In 2014, magnetized liner inertial fusion experiments with deuterium fuel at the Z machine produced about 10 high-energy neutrons, proving the feasibility of the MIF concept. The Z machine, operated by Sandia National Laboratories in the US, is the world's most powerful X-ray generator used for plasma physics and nuclear fusion research. This machine successfully demonstrated nuclear fusion using both magnetic fields and high pressure, proving that energy can be produced and converted to electricity directly. Helium Energy is a key player in fusion energy, signing a deal with Microsoft in 2023 to provide fusion energy by 2028. OpenAI CEO Sam Altman, an investor and chairman of Helium Energy, highlights the company's prominence in the tech world, valued at $5.4 billion despite not yet producing anything. Helium claims its Polaris reactor will be the first to generate electricity directly from fusion by 2028. The inspiration for this video came from a 2024 experiment at Los Alamos National Laboratory in the US, where 36 plasma jets were fired at 300 km/s to form a spherical plasma liner, compressing fuel for nuclear fusion. This was achieved in 2024 using superconducting magnets without the need for massive infrastructure or radiation shielding like tokamaks. Although electricity hasn't been produced yet with this method, we are experimentally very close.